Welcome to Lesson 10b, Viscous Decay of a Lined Vortex. In this lesson, we'll examine viscous decay of a lined vortex. We'll use cylindrical coordinates and generate a similarity equation, which we can then solve. Then we'll discuss diffusion+vorticity and plot some similarity profiles. This will be the third similarity solution we'll discuss. We already looked at Stokes' first problem and the diffusion of a vortex sheet. The present problem is kind of an axisymmetric version of this vortex sheet diffusion. Here's the setup of the problem. We start with a line vortex with u theta is some constant over r. We'll let constant k be gamma over 2 pi, where gamma is the circulation. So u theta is gamma over 2 pi r. This is the tangential velocity at t equals 0. As discussed previously, this is an irrotational flow. Fluid elements do not rotate as they revolve around the origin on circular streamlines. But the origin is a singularity. The velocity immediately to the right of the origin goes towards infinity, while that at the immediate left goes to infinity in the opposite direction. But at t equals 0, we suddenly allow viscous diffusion. You can think of it as turning on viscosity. The fluid is incompressible and Newtonian, two-dimensional, rotationally symmetric, which means nothing changes with theta, and gravity is ignored. We want to calculate the velocity field u theta as a function of r and t. To solve this problem, we'll start with the incompressible continuity equation in cylindrical coordinates. Well, this term goes away by our approximation 3, and this term goes away by our 2D approximation. Since this is the only term left, we can multiply both sides by r. Thus del r, RUR is 0, which we can integrate to get RUR is not a constant but some function of the other variable, which is time. Therefore UR is this function of time divided by r. But we know that in this flow, at the origin, since everything's rotationally symmetric, UR has to be 0. In other words, at r equals 0, UR equals 0 at all time. The only way this can be true, since r is in the denominator, is if f of t is equal to 0. Therefore, we conclude that UR equals 0 everywhere in this flow. This is the result of the continuity equation. Now we apply the navier-stokes equation in the theta direction, where we're using coordinates r theta z with velocity components ur, u theta, and uz. So let's write out the theta component of the navier-stokes equation. And now we apply our approximations and assumptions. UR is 0 by continuity, which we just showed. Approximation 3 gets rid of that term and that term. Any derivative with respect to theta. There's no z dependence by approximation 2. That also applies here. And again, UR is 0 by continuity. So we're left with 3 terms. But it turns out that you can use the reverse product rule with a little bit of algebra to combine these 2 terms into one. So I'll rewrite the equation as del u theta del t equal nu del r of 1 over r del r ru theta. And we'll call this equation 1. Equation 1 is a partial differential equation with one unknown or dependent variable u theta, which is a function of both radius r and time t. Equation 1 is first order in time from this term, but second order in r. Thus we need one boundary condition for t, namely at t equals 0, u theta is gamma over 2 pi r at all values of r. We need 2 boundary conditions for r. One of them is that as r goes to infinity, u theta must go to gamma over 2 pi r.
Sir, I would not have specified that boundary condition. I would have specified u theta goes to 0 as r goes to infinity. So why did you specify gamma over 2 pi r instead of 0?
Great question, Sean. The answer is that your boundary condition would work, but you would need to use L'Hopital's rule to generate our similarity boundary condition later. This boundary condition is much simpler to apply.
Thank you, sir.
We're basically saying that as we go far away, we still have the irrotational line vortex because viscous diffusion hasn't reached there yet. Our third boundary condition is that at r equals 0, u theta equals 0, and both of these are true for all time. all times greater than 0, since at time t equals 0 we turn on viscosity, and immediately u theta becomes 0 at the origin. These are our three boundary conditions corresponding to equation 1 in physical variables. But again, like the previous problems, there's no length scale, so we expect a similarity solution. So we need to define similarity variables. Let's set capital F of eta to be u theta over the original u theta at t equals 0. So capital F is a ratio of the actual u theta to the initial u theta. And what about eta? Since there's no length scale, we can use dimensional analysis to show that eta must be proportional to r squared over nu t. So let's set eta equal r squared over 4 nu t. This constant 4 is arbitrary, but as we'll see, it makes our algebra more simple. So this is our dependent similarity variable, and this is our independent similarity variable. We plug these into equation 1, and we do lots of algebra, including the chain rule for all the derivatives. I won't do all the algebra here, but I'll show you an example. Del eta del r is 2r over 4 nu t from here, but since eta is r squared over 4 nu t, we can write this as 2 eta over r. Similarly, del eta del t is negative r squared over 4 nu t squared, which again we can rewrite using eta as negative eta over t. Now we apply these to equation 1. For example, del u theta del t is del t of gamma over 2 pi r f, where we've used this equation for u theta. We put outside the derivative everything that's not a function of time, and then the time derivative is f prime del eta del t, which we get from up here as negative eta over t. So this is the left-hand side of 1. I'll leave the rest of this algebra for students to solve. If you do it correctly, you'll find that some terms cancel, and 2 nu gamma over pi, eta squared over r cubed, f double prime becomes the right-hand side of equation 1, and when we combine the left-hand side and right-hand side of 1 after a bit more algebra, where some of these constants cancel and the rest can be combined into etas and canceled again, equation 1 becomes f double prime plus f prime equals 0. This is a good practice problem that I like to say is good for a cold, rainy night. Students should be able to generate this equation, which I'll call 2. So we've achieved similarity in the equation, but recall that we also have to achieve similarity with the boundary conditions. Recall that at t equals 0, u theta is gamma over 2 pi r, which means that f equal 1, and at t equals 0, eta is infinity, since t appears in the denominator. Thus, f of infinity equal 1. That's our first boundary condition. Our second boundary condition, as r goes to infinity, u theta is gamma over 2 pi r, which again gives f equal 1, and since r is in the numerator of eta, this also has eta going to infinity. Thus, f of infinity is 1. These two match, which is what we always like to see in a similarity solution. Our third boundary condition was at r equals 0, u theta equals 0. Well, eta is 0 at r equals 0, and when u theta is 0, f equals 0. Thus, f of 0 equals 0. So we've reduced our equation from a PDE to an ODE, that's second order, and we've reduced the number of variables from 2, namely r and t, to 1, namely eta. The two boundary conditions agree here, and we need only two boundary conditions for equation 2, so we can state that similarity has been achieved. Now we need to solve equation 2. With its boundary conditions, f of 0 equals 0, and f infinity equal 1. Well, hopefully you recognize this equation as second-order, linear, homogeneous ODE with constant coefficients. This was one of the types of equations discussed in a previous lesson. To solve it, we rewrite as d squared plus d acting on f equals 0, where capital D is an abbreviation for the derivative of any order with respect to eta. And the nice thing about this is we can factor it. Here simply d times d plus 1 f equals 0. And the solution method involves finding the roots, which we typically call m equals 0 and m equal negative 1. In other words, m equals 0 and m equal negative 1 are the roots of this equation. And the solution, as you recall, is to say that f equals some constant c1 e to the first m, which is 0 times eta, plus some constant c2 e to the second m, which is -1 times eta. Well, e to the 0 is 1, so this becomes f equals c1 plus c2 e to the negative eta. Now let's apply our boundary conditions. At eta equal infinity, f equal 1, so 1 equal c1 plus e to the minus infinity is 0, therefore c1 equal 1. And at eta equals 0, f equals 0, or 0 equal 1, c1 is 1, plus c2, since when eta is 0, this term is 1. Thus, c2 is -1, and therefore f is 1 minus e to the negative eta. Quite a simple solution in similarity variables. This is our universal similarity solution. Universal meaning that it's valid at all r and t, since f is a function of eta, which is itself a function of r and t. We can plot this universal similarity curve, f as a function of eta. It turns out that it starts at 0 and asymptotes towards 1, where it gets pretty close to 1 by the time eta is about 5 or so. Well, this looks nothing like our decaying line vortex. That's because, as you recall, f of eta is u theta over gamma over 2 pi r. So this curve represents the ratio of the actual u theta over the initial u theta. If we go back to physical variables, by plugging in this definition of f, along with our definition of eta, which is r squared over 4 nu t, a little algebra yields u theta of r and t equal gamma over 2 pi r, 1 minus e to the negative r squared over 4 nu t. This is our final similarity solution in physical variables. Again, because of the similarity nature of this problem, this equation is valid for all r and all t. What does it look like? Well, we can plot u theta as a function of r and t. I'll plot u theta on the vertical axis and r on the horizontal axis and plot several profiles. At t equals 0, we have our irrotational line vortex with a singularity at the origin. But as time increases, the profile looks something like this as time keeps increasing, where we clearly see viscous diffusion. The effect of viscosity keeps spreading farther and farther radially. But all of these velocity profiles tend towards the initial profile, our line vortex, as r approaches infinity. I'll just comment here that for any one of these profiles, the curve is linear near the origin, and some people define an approximation called the Rankine vortex, which is solid body rotation until we hit this curve, and then it's the line vortex from there on. This is the Rankine vortex approximation, which is sometimes useful for simplified analysis. But here we have the actual profile shapes. Finally, let's look at vorticity. We can solve for the z component of vorticity by differentiation of the velocity field in cylindrical coordinates. I won't go through the math, but I'll plot omega z as a function of r and time. At t equals 0, there's an infinite spike of vorticity at the origin, which is a singularity. But as time increases, the curves start to spread out and decrease in height, as sketched here, with 0 slope near the origin, corresponding to solid body rotation near the origin. So we see a spread of vorticity, or a diffusion of vorticity, as time increases, corresponding to the spread of the velocity profiles as time increases. Finally, let's take a contour integral with some contour c, which will be a circle around the whole flow, centered at the origin, and I'll zoom out to show this. Let the circle be around the entire flow field, centered at the origin, and calculate the circulation. The circulation turns out to be gamma for any profile at any time, provided that we don't include this viscous core region, so that we're in the region of the irrotational outer flow, where you may recall that gamma is the integral over the closed contour c of u dot ds, where ds is a long curve c. This gives us gamma, of course, which is the circulation of our initial line vortex. In terms of the vorticity, if we pick one of these curves and integrate, the integral under the vorticity curve is also equal to gamma. This is the case even for the infinite spike at t equals 0 and for any of these other profiles. Thus we have an exact solution for viscous decay of a line vortex. Thank you for watching this video. Please subscribe to my YouTube channel for more videos.